Welcome to The Explainer. So I want you to imagine a protagonist that is constantly under siege, like literally battling for survival every single second of the day against these invisible stressors. Now, this isn't some new blockbuster movie. This is the dramatic, everyday reality of your very own cells. Today, we're going to dive deep into the micro-hero's journey, a cell's story of survival, injury, and sometimes tragic defeat.
Okay, let's just jump right in. Here's a quick roadmap of what we're covering today. We'll start with the language of suffering, move into the anatomy of a disease, look at the balancing act our cells have to perform, see what happens when they're pushed to the limit, and finally explore the point of no return.
All right, kicking things off with Section 1, the language of suffering, an introduction to pathology.
You know, it's actually really fascinating that the literal translation of the word we use to describe our hero's struggles, pathology, comes from the Greek words logos, meaning study, and pathos, meaning suffering. So it is quite literally the study of suffering. In the medical science world, we use it to describe the study of the morphologic, or basically the structural, changes that are caused by disease in our cells, tissues, and organs. Knowing that translation really gives you this profound emotional connection to the biology we're about to look at.
Now, when we look at this cellular suffering, we basically use two different lenses. First, there's general pathology. This is the study of the really basic, common reactions of cells and tissues to abnormal stimuli. We're talking about the things that underlie all diseases, like an acute inflammation response. It's the universal reaction regardless of what tissue it is. Then we have systemic pathology, and this is much more specific. It looks at how highly specialized organs and tissues respond to those abnormal stimuli. Think about how the heart specifically responds to an organ-specific disease, like a myocardial infarction, a heart attack.
Let's move right along to Section 2, anatomy of a disease, the blueprint of illness.
So how does an enemy actually attack our cell? Well, the disease process is studied under four core aspects. Actually, think of it kind of like a car breaking down. First, we have the cause, or etiology. That's the nail on the road. Second is the mechanism of development, or pathogenesis. That's the air slowly leaking out of the tire. Third, we see structural alterations, or morphologic changes, the tire physically going flat. And finally, the functional consequences, which give us the clinical significance. The car literally can't drive anymore. This four-step blueprint is absolutely crucial because it forms the core of how pathology understands disease.
Which brings us to Section 3, the balancing act, looking at the peaceful cell and the struggle.
Okay, so before the trouble even arrives, our microscopic protagonist is at its absolute happiest. This state is called homeostasis. It's when a cell is perfectly able to handle its normal, everyday physiologic demands. It maintains a perfectly steady state. This is the ultimate peaceful baseline for our cell. It's just going to work, doing its job, totally unbothered.
In this baseline state, the normal cell is just resting peacefully. Its structure is smooth, it's steady, it's perfectly equipped for its environment, totally balanced and ready for a completely normal day's work.
But what happens when that stress just becomes way too much? When the environment completely changes or the workload suddenly spikes way beyond what is normal? Well, our peaceful baseline is shattered and the hero's journey truly begins.
When it's hit with excessive physiologic stress or pathological stimuli, the cell doesn't just throw in the towel right away. No way. It fights back by altering its steady state. We call this cellular adaptation. Think of it like suddenly being handed the workload of 3 people at a really stressful job. You have to fundamentally adapt your entire routine just to survive, right? Well, to survive, our cells execute these reversible structural changes. Depending on the stressor, they might multiply their numbers, that's hyperplasia. They might bulk up their size, hypertrophy. They could shrink away to conserve energy, atrophy. Or they might even completely alter their cellular identity, which is known as metaplasia. Compared to that baseline peaceful state we talked about earlier, a cell subjected to stress completely changes its physical structure to cope. It's literally pushed out of its comfort zone, so it adapts to the harsh new environment and enters this altered but still steady state. It's surviving.
But as we all know, adaptation definitely has its limits. Let's look at Section 4, push to the limit, the breaking point. So here is where those amazing adaptation strategies finally start to fail. Cell injury occurs at the exact moment when the cell can no longer adapt. The limits of its adaptive response to that stressful stimulus have simply been maxed out. This is the exact breaking point where stress transforms from a manageable, adapted challenge into an active sequence of events that we label cell injury.
Once it's injured, our hero is standing at a major crossroads with two very different paths. On one side, we have reversible injury. If the harmful stimulus is removed, the structural and functional changes caused by the injury can actually revert right back to normal. The hero recovers and lives to fight another day. But on the other side is the tragic path, irreversible injury. Here, the damage is so profound that even if you take away the bad stimulus, the changes just cannot be reversed. This path inevitably leads to cell death.
At this stage, those intense structural changes are just undeniable. The cell's physical integrity is heavily compromised, and its shape distorts dramatically. You can see the cell desperately trying to hold on before it crosses that dark line into irreversibility. It is the visual reality of suffering at a microscopic level.
And that brings us to our final chapter. Section 5, The Point of No Return, Final Fates.
So, what are the ultimate outcomes if a cell is just pushed way too far by sublethal or chronic injurious stimuli? Well, it can physically give up in a few fascinating, albeit kind of grim ways. First, through intracellular accumulations. Because of metabolic derangements, the cell might start hoarding materials. This could be normal cellular constituents, abnormal ones, or even pigments. Second, it might suffer lingering subcellular alterations, which are essentially the residual effects or the scars of the injury. And finally, the ultimate point of no return, cell death. This happens either through uncontrolled necrosis or a highly programmed self-destruction process called apoptosis. But let's actually shift focus for a second to everyday reality. Because even without a sudden catastrophic attack, our cells are facing another relentless opponent: time. Cell aging represents the progressive accumulation of sublethal injuries over years and years. It eventually manifests as an inadequate response to injury or ultimately cell death. And just look at the factors influencing this: your genetics, your diet, your social environment, and underlying diseases like atherosclerosis, diabetes, and osteoarthritis. It is quite literally a lifetime of minor battle scars.